All right, last but not least, let's talk about confidence intervals around the variance, or really the standard deviation. I mean, we use the variance a bunch. I don't want to say, oh, it's useless and it only gets us through to the standard deviation. That's not true. There's tons of parametric statistics that uses the variance that you have to have the variance for, and they're very clever. But by and large, what we need this for is to be able to figure out the standard deviation. Now, I'm not going to get too crazy in this section because there are some relatively advanced topics going on here. I'm going to give you formulas. I'm going to show you how to use them, and we'll talk about them. Now, remember, variance distributes itself. All right? Remember, first and foremost, sample variances are an unbiased estimator, right? And they distribute themselves. If I do a whole bunch of them and I take the average of them, then I end up with this weird curve that does this. All right, now it's on, we have an x and a y. It's not just like we only care about the x-axis like we did with the others. This should be more curved, by the way. That looks a little too linear. Looks like this. It is not a normal curve. It is an asymmetric curve. And the reason is, think about it. We know for a fact that variances are always positive. They have to be. They have no choice. This is sometimes referred to as a chi-squared curve. Chi-squared. So chi-squared. It's called the chi-squared curve. It's not symmetric, okay? And this thing changes just like t. This thing will change with degrees of freedom. As degrees of freedom increase, so this is dependent on degrees of freedom. Let's change colors real quick. Let's say that, well, let's go back to black. Let's say that this guy right here is degrees of freedom equal 10. All right? What would happen is, as degrees of freedom increase, what you end up with is a curve that looks far more normal, even though it can't be because it's cut off over there. It can't go all the way to negative infinity theoretically. But let's say that this is degrees of freedom of, say, 50. Now, the problem with this family of curves, just like we had with the t-curves, the problem is that it's not symmetric. So remember back in the day when we were putzing around, and all we did, if we wanted to figure out confidence intervals around proportions and around means, we took p hat minus error and p hat plus error, or we took x bar minus the error, because the error was the same on both sides because they came from the normal curve, and x bar plus the error. In other words, these guys were always the same value. These guys were, wait, I didn't mean to write it like that. Try that again. Sorry. I wrote my arrows the wrong way. These guys were always the same values. And these guys were all the same values because they came from a curve that was symmetric. So I got a value here and a value here. Well, that's not going to work here, because this curve doesn't work like that. So when I go to find my values, I got to get a little more complicated, okay? All right, I'm going to show you how to do this, and we'll do it almost exclusively from the chart. Now, before we do that, I know that I run a risk of confusing you here, but we're going to use just the formula first and foremost. I'm going to give you the chi-squared formula. So chi-squared is equal to n minus 1 times the standard deviation of the sample divided by sigma squared. That is the formula that produces this curve, okay? So if you think about it, if I'm trying to find a confidence interval around sigma, watch what happens. A super simple cross multiplication, I get sigma squared equals n minus 1 times s squared divided by chi-squared. Now, this chi-squared value is where we get our critical values from. All right, and we're going to use our table to do that. Now, again, the asymmetry of this thing is kind of a pain in the butt. And I'm going to give you the overall formula right now. So this chi-squared creates this family of curves. And then we did a little algebra like we did before when we were trying to figure out the error values for means and for proportions. The formula for this is actually sigma squared is going to live between, now it's going to be n minus 1 times the sample standard deviation squared divided by chi-squared, except this is going to be the chi-squared value on the left. Now, think of this value right here as the chi-squared value on the left. Then I'm going to have n minus 1 times s squared, and I'm going to divide that by the chi-squared value on the right. And we have to delineate these. We have to separate them because of that asymmetry. So this is chi-squared on the right. Now, let me draw this out a little bit for you guys real quick, just so you can look at this. I want to make sure you get this. Even though it's all formulaically driven, nothing's too crazy. All right, here's my chi-squared. Okay? Now again, asymmetry. Ooh, that's a badly drawn chi-squared. It looks more normal. That's a bummer. That's not what I wanted. Let me redraw this guy just a little bit so we get a little more exaggeration. Okay? And let's say, for example, that I want a 95% confidence interval. Now, here's what I'm going to have to do. I'm going to have to figure out my chi-squared on the left and my chi-squared on the right. Now, notice the areas here, what I need is, I'm going to need 0.025 worth of area on this guy, and I'm going to need 0.025 area on this guy as well. But because the areas don't look the same, I mean, just by looking at this curve, it's confusing. So what I have to do is I'm going to dig in on my table, and my table's, I'll show you guys how to do this. Now, the most important thing that you get out of this is that the hardest one to find is this guy right here. So think about this. So I'm doing a 95% confidence interval. Basically, the way the tables work is they always give areas to the right of the critical value. So when I go to look for the area to the right of the critical value, and really theoretically this goes into infinity, so this 2 would go into infinity, all of this is 97.5% or 0.975, but that includes all of the area all the way to infinity. Now when I find this guy, it's easy. I just go dig around for 0.025 in my chart, just like the other charts work. Now, let's do that right now. We are going to find these critical values, this chi-squared left and this chi-squared right. Just now, I'll change the color of my pen, and we'll go to a chi-squared table. Let's see if I can find a chi-squared table around here somewhere. Man, I got all kinds of stuff open, don't I? All right, you ready? Oh, there's a chi-squared distribution. Look at this. All right, I'll show you both of them. Here's the shape of the curve. Right? This is what it looks like. These are my degrees of freedom. Remember, degrees of freedom come into play whenever you're talking about a sample standard deviation. You have to respect that. Okay? And then check this out. Okay. I suppose I should come up with a degree of freedom for this guy. So let me pop him open real quick. Bamboo paper. Let's say that, I don't know, let's make degrees of freedom, let's make it 20. All right, now watch how this works. It's not so bad. I'm going to find my chi-squared left, and I'm going to find my chi-squared right. And watch what happens. So let's see. If it's 95%, that means that if my chi-squared left is going to have an area, this tail over here is going to be 0.025 to the left. But I want everything to the right, which is 0.975. But looky here. Right here it says 0.975. So I go down, what did I say my degrees of freedom were? It was 20, wasn't it? Let's pop that thing back up again. Degrees of freedom are 20. So the value on the left is going to be 9.591. 9.591. And the value on the right is going to be the value that produces 0.025. See? This chart gives it to me to the right. So 0.025, I stumble down to degrees of freedom to the right, which is 34.170. Now you may say, wow, Ripley, those are some big numbers. 34, what was it? 34, where the heck am I? 34.170. So 34.170. I'll just write it as 34.17. Okay? Why are these so big? Why are they so huge? Well, we're talking about variance, right? Variance is a value squared. So any number, if you've got a variance if you've got a standard deviation that's greater than 1, then when you square it, you're going to get a bigger number. That's why these numbers are so huge. Now, let me show you. This is I used that one because I wanted one with a nice picture on the top. But look, we'll get exactly the same values. Look, so here's my degrees of freedom. Down the column, across the rows is the area to the right of the value. At 0.975, if I go down to degrees of freedom, I get 9.591. If I go to 0.025 and I go down the column, I get 34.170. So that skill right there, in and of itself, is the most important skill that you need to be able to do. Because really, guys, look at the formula. I mean, the formula is pretty straightforward. And we'll do one of those guys here in just a second. Okay?